Hello everyone, in this short video, I will be discussing how our group optimized a classifier for loan approval predictions. We will cover feature engineering, model compression, hyperparameter tuning, and more. So we started by cleaning and preparing our data. One of the first things we did was handle outliers in numerical features like a person age, person income, and loan amount. Outlier can really throw off a model's performance because they distort the data distribution and can mislead the algorithm. To tackle this, we use the two key rules to identify and remove these outliers. And this step made our data more representative of the real-world scenario, and which will ultimately lead to better predictions. And here is the loan status class distribution after the outlier removal. This is the correlation matrix of training data. Next, we focused on feature engineering to make the data more meaningful for the model. The binary categorical feature like person, gender, and the previous loan default on file, we use label encoding. It covers the category values into numerical ones. And for the feature with multiple categories like person education and loan intent, we use the one-hot encoding. And this technique creates separate binary columns for each categories and preserving the category code nature of the data without implying any order or hierarchy. These transformations made the data more interpretable for the model and improved prediction quality. Now let's talk about the models we tested. So we compared three models, the logistic regression, random forest, and cat boost. So for the logistic regression, we think it is simple and interpretable, which makes it great for the quick decision making, and it is computationally efficient. However, it assumes a linear relationship between feature and the target variables, which isn't always realistic in complex data set like ours. Well, it is easy to explain to stakeholders. It might miss out on capture nonlinear patterns, which can limit the performance in terms of the metrics like the F1 score. Random forest is a more complex linear model that excels at capturing some relationship in the data, and it works by aggregating multiple decision trees, which reduce the variance and improve the generalization. But how about the downside? It can be comparatively expensive and harder to interpret compared to the logistic regression. And for loan approvals, it's great to finding the complex patterns, but explaining its decision to stakeholders can be a challenge. So the model that stood out is the cat boost model. This is because of its ability to handle the category data directly and without needing extensive preprocessing. It also uses techniques like ordered boosting, which improves the performance. In a business context, this is a huge advantage because it can make more accurate predictions based on categorical features. And it's a powerful tool for loan approval prediction. So to get the best performance out of our model, we turn the hyperparameters like the number of interactions, deep depth, and learning rate. We use the techniques like grid search and random search to find the optimal values. Before tuning, the models were underperforming, but after tuning, we saw a significant improvement in the F1 scores. For example, adjusting the tree depth in cat boost allowed the model to capture more complex patterns without overfitting. We also monitored for overfitting and underfitting by plotting learning curves. If the learning error was much lower than the valid error and the gap was widening, it signaled that the overfitting. To fix this, we could reduce the model's complexity, like decreasing the tree depth. On the other hand, if the model was underfitting, we could increase its complexity or add more features. To evaluate our models, we use tools like confusion matrix and precession recall curves. In loan approval, the first positive, which means approving a loan that will default, can lead to financial loss. While false negatives, the rejecting a loan that would have been repaid, means that missing the business opportunities. And the precession recall curves help us find the right balance between precession and recall. For example, if false balance between precession and recall. For example, if false positive were costly, we might raise the approval threshold to reduce them, even if it means accepting a lower recall. Once the model is in production, it is critical for us to monitor its performance. And we would regularly calculate the metrics like F1 scores, precession, and recalls on new data. To detect data drift, where the distribution on feature change over time, we'd monitor the feature distributions. For example, if the distribution of the person income shifts significantly, it could indicate the drift. In such case, we'd retain the model on updated data to maintain its accuracy. And if we have more time and resources, we'd incorporate external data like macroeconomic indicators like GDP growth rate or unemployment rate. This could provide valuable context about the economic environment in which loans are issued. We'd also explore using credit data to get a more accurate picture of borrowers' creditworthiness. So, in sum, this process not only improves our classifiers' accuracy, but also gives us the insight in how to make better loan approval decisions. Thank you for your listening. Now, I hope you found this workflow helpful.